in. Last time we looked in section 1.5 at quadratics, y equals ax squared plus bx plus c, and looked at a little bit of analysis of quadratics, mainly where is the vertex, where are the zeros, some work with that. Questions from those problems? 13. So 13, we're given the height of a ball thrown in the air is given by, so we don't have to worry about where they come up with this formula. I believe it's fairly accurate. Looking at the physics of the situation, but that's the height at any time, and we want to know, well, how high is the ball when it's thrown, what's the maximum height, and how far from the thrower does the ball strike the ground. So x is the horizontal distance. So we've got our height versus the horizontal distance. So in A, we're asked, well, how high is the ball when it's thrown? So in terms of when it's thrown, what is that in terms of the variables we're talking about here?
Y-intercept.
The y-intercept, what happens when x is 0, right at the start. So when thrown, is our y-intercept. It's what happens when x equals 0, which is going to be 3. So it starts at 3 feet. So I don't know, maybe they're throwing an underhand, or they're just really short, or sidearm or something. But it starts from 3 feet. B then asks, well, what's the maximum height of the ball? Now, in terms of that question, what are we going to need to find? The vertex. So we need the vertex. The x-coordinate of the vertex is at negative b over 2a. So in this case, negative 6 over 2 times negative a 12th. Negative 6 over negative 1/6 is actually x equals 36. But that's not the height. That's the horizontal position when we achieve the maximum height. The maximum height is actually the height we get at 36. We plug that in here, negative 1/12 times 36 squared plus 6 times 36 plus 3. We could have pulled out our calculator here. Here I definitely think we probably want to pull it out. So let's see. Negative 1/12 times 36 squared plus 6 times 36 plus 3, 111. That's our maximum height. It occurs 36 feet out here. So height of 36, or horizontal distance of 36. Our height is the maximum of 111. And then it's going to start coming back down. And C, they ask, well, how far from the thrower does the ball strike the ground? So it's going to come back down and eventually come over here and hit the ground. So in C, for hitting the ground, we need to figure out, well, where is the height 0? Now, here our setup's a little bit different than sometimes, because we didn't start at a height 0. We can't just say, well, if we took 36 feet to go up, it'd take 36 more feet to come down. By symmetry, at 36 more feet, so by the time we get out here to 72, we'll be back to a height of 3. By symmetry, I guess the height of 3 is more up here. But we want to know, well, when does it hit the ground? So we need to solve this quadratic. Negative 1/12 x squared plus 6 times x plus 3 equals 0. With the fraction in there, I really don't want to try to factor this. And also kind of looking at this, I hide the zeros a little bit before 0 and sometime a little bit past 72. I don't think I'm going to get easy answers from this anyway. So let's just go straight to the quadratic formula. X is negative b plus or minus the square root b squared minus 4ac all over 2a. So negative 6 plus or minus. Let's see. 6 squared minus 4 times negative 1/12 times 4, no, times 3. So we're looking at the square root of 37. Square root of 37, 6.08. So negative 6 plus that is one answer. I believe that's the minus that I would be interested in. And then divide that by negative 1/6. We get 72.5 roughly. And also minus 0.5 if we would do the other. So negative 6 plus 6.0 whatever divided by negative 1/12 will give us the negative 0.05. The other one gives us the 72.5, so that's when it hits the ground next. Yes?
Is there a way, so like I just graphed it, and then I just went second calc and went to the value, and then it just gave me what I could do for x. Can I do that, but have the y value, so I can just put y equals 0, and then get 72.5?
I don't think so. Let me,
So
let's put this in here. So we've got negative, what was it, 1/12 x squared plus 6x plus 3. And so if we graph it, first thing when we graph it, we're probably going to realize we can't see most of the graph. So we need to kind of adjust the window a little bit. Based on our work we've done, let's take x up to 80 and y up to 120. And let's go x in steps of 10, y in steps of 10. So now if we graph it,
I think you had x.
yeah, I missed something because that's not what I was looking for.
Yeah,
Window 8, 0. And so there we see, under calc, since we're actually looking for a 0, there's the calculate the 0.
Yeah.
So we could say calc 0 here. We kind of have to give it a bit of an idea of where we think the 0 is. Doesn't have to be extremely accurate, but we can trace along here and realize, well, we're positive at some point. A little bit later, the function's negative. Somewhere in between, there should be 0. It'll do some work, and it should give us exactly the same answer with that. So we can calculate the 0. What we can also, with this, under the calculate menu, which is the second trace, calculate the maximum, which is what we wanted for B. Where is the maximum? And again, we kind of have to give it a bit of a heads up where we think it is, which from the graph we can kind of tell roughly where it is. It's somewhere between there and there, maybe there, and it'll do some work and tells us where the maximum is, 35.999997. It rounds off. We figured out it was actually at x equals 36 with 111 feet. It does give 111. It doesn't give it right at x equals 36. It should be 36 exactly. So what it's doing is some rounding and different things, and so occasionally, the answer may look a little bit weird on that.
So just second calc and then go over and then get to the tons.
Second calc, we can actually calculate the value at any point on the curve. We can find the zeros, maximum, minimums. If we had two curves, where do they intersect? And actually, number 6, the derivative, is something we will get to in chapter 2. Number 7, the integral, we'll get to in chapter 3. So the calculator will actually do a lot of the things that we're interested in doing. And so, in a sense, some of what we're doing, yes, could be done by the calculator, but we're trying to develop an understanding of what exactly we're looking for. So, on the quadratic, the things we are typically looking for is, where do we hit 0, where do we hit the maximum, and what is that maximum value? And we're not interested in it here, but tying into where we're headed, we're also going to be interested in, if I extend this out a little bit, where the quadratic is positive and where the quadratic is negative. So the quadratic's negative outside of the 2 zeros in this case, and positive in between, because we're above the axis. And certainly if you had a business and this was your profit, you'd like to know on what interval of time are you making money and where are you not making money. So there are times we're definitely interested in figuring out where our function is positive and where it's negative. And as we see here from the quadratic, it's something we're going to continue to see in the next section. Between 2 zeros, it's always either positive or it's negative. Here it's positive, but if the quadratic were something like this, between the 2 zeros it's negative, and outside the 2 zeros it's positive. But where the zeros are really kind of key in figuring out, well, where is it positive and negative? And if we've got the graph, we can figure that out. If we don't have the graph, well, if we can figure out where the zeros are, that is part of our work in figuring out where it's positive and where it's negative. And we'll be expanding on that today in 1.6. Other questions from 1.5? Okay. Well, if you've got that homework done and want to pass it up, that's fine, or if you need a little bit more time to finish it up, get to my office later today. I'll put it in my grade, I'll separate it out, thanks. Did we lose some?
Yeah,
Certainly don't want to lose any
I
more
don't
here.
know.
Okay. Now is a good time as you look to double check grades. I've been having a grader grade these, and definitely I've noticed some of you are looking at them to see. That's a good thing because he can make some mistakes or maybe grade it slightly differently than I would in terms of that. But also, he's got a sheet, he records them. I try to get all those brought over correctly, but there are times mistakes can be made, especially if you happen to get a 10, because I get entering grades 10, 10, 10. Sometimes it doesn't take the, much like our clickers, it doesn't take the first button pushed, it only takes the second. Actually, the clicker usually takes the first button and then not the second. The blackboard usually takes the second and not the first. And 10 suddenly becomes a 0. So I try to watch that, but it is much easier to correct that now. than it would be later. Also in terms of your participation, for those that have missed with baseball and different things, on the absence it initially goes in as a 0. On your next time back in class, I average your participation from that day and the day before the absence to replace. So on any justified absence, that's what I do. It initially goes in as 0, and then I average the absence or the participation before and after. So again, that I try to watch, but again, it's easier to make corrections now if you decide, wait a minute, I still got a 0 there. I thought Doc Hopkins knew I wasn't going to be here because of, but it's much easier to think back a week or two than in May and think, well, you know, that day back in February, I think I was gone for a good reason. It's just much easier to get that taken care of now. And participation typically is a 6 out of 6, unless you're just not here, in which case it's 0 out of 6, or if you have fewer than 50% of the clicker questions answered. That's kind of what I look at and see on that. And definitely check your homework as well. So today we're going to be moving on into section 1.6, looking first at polynomial functions, and then also just a little bit at rational functions. The polynomial functions, instead of stopping, say, just with an x squared, a constant term, an x squared, we throw in some higher power terms of x. And so as we first sort of describe it, it looks very much like a jumble of letters. Essentially all we're saying here, though, is we've got some number called x times x sub n plus some other number times x sub n minus 1 on down. So we have integer powers of x, and typically they're bigger than 2. If they were just 2 as the biggest power, that's quadratic. So an example here would be this: 6x to the 4th minus 5x squared plus 2x minus 5. That would be a polynomial. Poly meaning many, so this is many terms. This one, in fact, has 4 terms. Sometimes we might even say it has 5 terms because we're missing an x cubed between, and so we could say x cubed has a coefficient of 0, which we wouldn't write. 6 is the highest, the coefficient of x to the 4th, coefficient of minus 5, a coefficient of 2, and a coefficient of minus 5. So we've got coefficients. We see here 4 terms, 4 non-zero terms. We normally don't write down the 0 terms. The only reason we really maybe focus on a 0 term is if it looks like it's missing. Certainly we wouldn't put on here, 0x to the 5th, 0x to the 6th, 0x to the 7th. It's probably could be looked at that way, but usually we look at it just for the highest power of x, and that we call the degree of the polynomial. So this one is of degree 4, because our highest power of x is 4 in this case. And the leading term is the term with the highest power. So 6x to the 4th is the leading term. In a quadratic, this is always the leading term. And every quadratic is of degree 2. Well, unlike quadratics where the graphs were very predictable, they were a parabola either opening up or down, and the sign of A would tell us whether it's opening up or down, polynomials are much more complicated. So the leading term is important in terms of one of the questions we're going to be interested in, but the graph in general is much more complicated. Yet we're still looking for some information here. And the book entitles this either short-run behavior or long-run behavior. Short-run behavior, we're interested in our polynomial, where do we cross the axis? Where do we cross the y-axis? Because just like with the quadratic, where the output is 0 is important. Excuse me, where the input is 0 is important. More important, though, is where do we cross the x-axis, where is the output 0? And that's going to be much harder to find. If we could factor it, we could find the intercepts much like quadratics. One of the factors has got to be 0. So when we factor a quadratic, if it had 2 factors, it would have 2 factors. Either the first or second factor is 0. Well, that's not the case in polynomials. And so if all we wanted was a graph, going to some technology is probably an easier way to do that. So this first polynomial, what did I say? It was 6x to the fourth minus 5x squared plus 3x minus 5. Turns out this particular one only has 2 zeros. But notice, like I commented for the quadratic, between the 2 zeros, the sign is always the same. In this case, it's always negative. Outside the zeros, on past 1 0, it's the same. On past the other 0, it's the same. If we think about that, well, the only way we could go from positive to negative with a function is to go through 0. So if we can figure out where the zeros are, we'll go a long way to figuring out, well, where is this function positive and where is it negative? Now, finding those zeros in general is much more complicated because that is much harder to factor. In fact, as we look at this, it looks like at 1 we might have a 0, but it's not exactly at 1. 6 minus 5 plus 3 minus 5 is not 0. So it's much harder to analyze. But if it's given to us in factored form, well, we can definitely figure out where the zeros would be. Our main interest in polynomials is really going to be figuring out where is the polynomial positive, where is it negative. And we'll use where it's 0 to help us in that. So for example, here's a polynomial. This one happens to be a 3rd degree polynomial. And so we're interested in where it's positive and where it's negative. And there are 2 forms we can have this question. One form is, here's an interval. Tell me something about the function. So that's the form we have here. For the interval 1.2 to 5.2, and that's the interval on the input, what can we say about the function? Maybe everybody. Now let's see, most people said this function is negative. So we're interested here just the interval from 1.2 to 5.2. So from here to there, and those are 2 places where it definitely looks like the function is 0, and all the way along that, the function is below the axis, the function is negative. So our function here is negative. So in this way of posing the question, it's, look just at this portion of the interval, what is the feature we're seeing? The other way this question could be asked is, this function is positive on what interval? So we're looking for a feature and then trying to describe where do we see that feature. So here we're interested where the function is positive. The function is positive here, so on this interval, and then also over here. We see the function's positive. So we're on the interval from minus 2.7 to 1.2, but not only, also from 5.2 on. So D is our answer here. So we can see the feature. And notice, for both positive and negative, where this function is 0 is an important part of the process. Because that's the only place we can switch from negative, positive, positive, negative. And that idea is going to be helpful not only in graphing the function as it is, but when we get into the idea of the derivative. Where the derivative is positive will tell us something about the function. Where the derivative is negative will tell us something about the function. So we're still going to be interested in figuring out when a fairly complicated function is positive and when it's negative. And it's a bit more complicated than students often make it. It's not too complicated, but it is a different way of thinking about it than students often approach the problem. So, we like to figure out, well, can we do this from the equation? So, if the polynomial factors easily, or we start in factored form, we should be able to figure out a little bit, enough information about this function to answer this question. Where is this product positive? Greater than 0 or positive. Two different ways we could say the same thing. That's the question we want to answer. For what x values is this expression positive? Well, we're going to start this thinking about the graph. If we just knew where it was 0, between any two zeros, it's either above or it's below. So let's figure out where the zeros are first. Since it's in factored form, figuring out where the zeros is a lot like what we did with quadratics. One of the factors has got to be 0. So if we look at the first one, x plus 1, we can solve that x equals negative 1. That's one place this polynomial is 0. Well, there are a couple more factors, so let's look at those. So x minus 2 equals 0. So what does that tell us about x? Well, if x minus 2 is 0, x has to be 2. That's what would solve x minus 2 equals 0. So x equals 2 is another place this polynomial is 0. Well, we've got one more factor. Based on that factor, where else is this polynomial going to be 0? Also be 0 where the last factor, x plus 4, is 0. That happens when x is negative 4. So since they gave this to us in factored form, we can figure out the three places this polynomial is 0. Now, the question was not, where is this polynomial 0? The question is, well, where is this polynomial positive? But thinking in terms of the graph's going to have to go through these 3 points. So there are a number of things it could do. Maybe it just comes and touches one. We don't really know. Well, we're going to have to analyze the polynomial more. But it is not just an analysis of the 3 factors individually. It's how do they all combine. But once we know the 3 places the polynomial is 0, those are the only places we could change sign. And we don't even know yet if it actually does or not. but that's the only place it could. I mean, with a quadratic, it is possible you'd come down and touch 0 and then leave and not actually change sign. That can also happen with polynomials. So we know how the real line is divided into 4 intervals. Before -4, between -4 and -1, between -1 and 2, and on past 2. And we just want to know, well, what's the sign on each of those 4 intervals? So we really just have to test any point in here. If it's positive at one point, it's positive throughout. If it's negative at one point, it's negative throughout. Similarly for each piece. So the book uses a table to help organize our analysis. So it looks at our 4 intervals. And notice we'll always have one more interval than we have zeros. 1 0 divides it into 2 intervals. And in each interval, we're going to pick a point to test at. So in this first one, negative infinity to -4, I've decided, well, let's test it at -5. Any point in that interval is fine. Key thing, though, is you've got to be sure you're in that interval. Here's the function we're looking with. So if we plug -5 into that function, -5 in for all the x's, I get -4 squared times -7 times -1. I really don't care the exact value of this. I am much, much more concerned in, is it positive or negative? So a negative squared will be positive, times a negative times a negative. The result will be positive. It is positive 112. But for now, at least, we are just really trying to figure out the sign of f. F is positive here. So we pick a point in each interval, we test the function at that point and decide, is the function positive or negative? I already told you the answer to this one. This is positive. Our function's greater than 0. Well, let's continue that. So let's move to the next interval. Tell me, of these 4 options, which of these points is in the next interval, from -4 to -1? Now, there are actually lots of points between -4 and -1. The easiest ones would be -3 or -2. So B here, -2 is in that interval. -1 is not in the interval, it's on the edge. -6 is not in the interval, and 2 is not in the interval. So of the choices I gave you, only -2 is in the interval. We're going to evaluate the function then at -2. As we do that, do we get something that's A greater than 0 or B less than 0? at, let's see, -1 squared times -4 times 2, positive, negative, positive. This is actually going to be negative, less than 0. So we have to watch our signs carefully. The exact value, I believe, is -8. I don't care the exact value at this point. So we're really not looking to get an accurate graph in terms of how low and how high it goes. We are just trying to get an accurate sense of, are we above the x-axis or below? Is the function positive or is it negative? Between -4 and -1, the function's negative. So far, we know the function is doing something like this. Starts off positive. We only test 1 point, but that's okay, because there's no other place it will change signs. It switches to negative, and we work to continue to fill in the table. So we pick a point in the next interval. So which of these points is in the interval from -1 to 2? And of the options given, only 0 is in the next interval. -1 and 2 are both on the endpoints. So we'll pick 0 as our next endpoint, and we'll do the same type of analysis. Can we figure out what the value of the function is there, or at least what the sign is there? So we get 1 squared times -2 times 4. Turns out that's still negative. Still less than 0 there. So it doesn't always alternate. This is a case that comes up, just touches the 0 and then goes back down. How far down, we don't know yet. Once we learn some stuff about derivatives, we'll be in a position we can answer that question of how far down and where is that lowest point. But for now, we are just looking, where are we above the axis, where are we below the axis. And one more then. So which point is in the interval from 2 to 8, or excuse me, 2 to infinity? And of the options given, it is 3 is the only one. There are lots of points we could use. 3, 4, 27, pi. There are lots of options we can use. Normally we would pick something easy, but we have to be sure it's in the interval. And we'll do the same thing there. So what about the value of f of 3? And f of 3 is positive. 4 squared times 1 times 7, everything's positive. F of 3 is positive. Our function goes back up above the axis. So it's greater than 0 there. So we've tested now. We were interested in, for this particular case, where is this positive? We actually tested every interval and found out, well, some of them are not what we want, but some of them are. The intervals we want is this interval where it's positive and this interval. So it is not just the interval from 2 on. It's also the interval from negative infinity to negative 4. That's where our function's positive. That's our original question. So we can find which intervals give the solution. We can certainly go to a graph and kind of double check that we've got that correct. So if we were to graph, turn that one off, and graph this one, x plus 1 squared, x minus 2, x plus 4. We get a graph that looks somewhat like we had. Again, we are interested in where are we above the axis, where are we below. We are not at all in a position to figure out where exactly are these valleys. We did find out a peak, since we just come up and touch 0 and then go back to negative. We did find a peak there at negative 1, but we're not in a position to find the peaks or valleys. We could, with zooming in some, figure it out a little bit on the graphing calculator, ask it, and it could find the min value and where it occurs. We will get to that point in the course of figuring out, well, where are those extreme values? But for now, our focus is, where is the function positive, where's the function negative? Because that then does tell us something about the graph. And we could look at the graph and do that. Now, I think we've got time to try this. So, for x minus 3 squared, x plus 1, 2x minus 5. Work on this, if you want to get together with 1 or 2 people to work on this. We were trying to solve this inequality. So in groups of 2 or 3, work through this problem. If you've got questions, ask, because the process here, it's not just, oh, one of the factors has to be negative. It's how did the 3 factors work together, and rather than analyzing that, I find in the long run it's much easier if we think of where are the zeros, what's happening between every 0, and actually getting an idea of what the graph looks like. So, I think we can take about 10 minutes for you to kind of work through this and see, and then we'll talk about it. We do have a little bit more in the section as well.
you pick one between negative 1 and 2 and a half. So, I'm gonna pick 1. I'm gonna plug it in first. Yep.
Dr. Hopkins, did you do my part? I was trying to see why this question here. I just don't know how can where I go from here. Like, I don't remember.
So where is that going to be equal 0?
When is it going to equal 0? When will it equal 0, I guess. But,
So one of the factors will have to be 0. So let's just look at that one. Where's that factor going to be 0? The value of x.
the value of S, it has to be, want to be negative.
I mean, so for x minus 3 to equal 0,
Oh, okay. S minus, okay, we did it out. Like, S minus 3. Plus.
I mean, we want x minus 3 to equal 0.
Okay.
So what's x going to have to be?
Oh, it's gonna have to be.
Oh, -3.
No, wait. Okay.
Square. It's not.
We want S minus 3 equals 0.
0 plus 1.
Then we would have
2
to
times
do
0. Times -5.
plus 3.
Wow.
Add 3 to both sides, so x equals 3.
Okay.
So that's one of the places that this equals 0. So that's one place on the number line we could switch from positive to negative, negative to positive. We don't know what, but we at least know one of the places it could switch. So what about on this one? Where is that going to be 0?
Oh, S plus 1 minus 3.
Not by a lot.
No, we minus 1 on both sides.
So you get x equals. So that's another place that we could switch.
Okay.
And what about that one? That one I would just go ahead and start writing down.
Yeah.
Yeah, I did. I could both sides.
They then graphed it out too.
And what?
So look at this.
So that's another place. So there are 3 places the function could equal 0. Between those zeros, it's either always positive or it's always negative. We just have to figure out which. So you can have to figure out where those 3 zeros are. What 4 intervals do we get?
Yeah, just whatever.
Yeah, that's the, but you have to square it. So it's 0.065.
So I can just read you what values I use. I use -2, 0, 2.75, and 4. I just worked out enough for it.
5.5 minus 5.
So it would be.
So 0.5.
Yeah. So, yeah, do you know roughly where 5 over 2 is?
I'm not finding the number, like for this one, I didn't find the number, I just like looked at it, and like, alright, this is positive, this is positive, this is negative.
Okay, so,
Yeah, pretty close to 3, but yeah, 2.5. So,
and the second
so we've
one,
got
the
4
last
intervals.
one would be
4
positive
negative 1.
also.
Between -1 and 2.5.
No, no.
Oh, really?
Yeah,
Between
it'd be
2.5 and 3.
so it'd be 3.
And then past 3.
Oh, you're good. You're good.
So, I mean, we know 3 places it is 0. So now we got to decide, okay, before -1, are we above or below x? And between the 2,
Yes.
are we above or below?
So,
2.5 and 3 are we
like,
above?
that's why I did 2.75 for in that middle. And so it's like
We
point.
really only want to know below, but
So it's just hovering over.
we'll analyze all the intervals just to make sure we don't miss anywhere it's actually below.
Can't wait till we get deeper into the year.
So if we pick, say, what's a point in this first interval before -1? Okay. So at -2
If it helps,
is
he
this
has
something
to
about or negative?
test that thing.
That's the next. So we kind of, we figure out how it splits. We pick a point in one of the intervals. We figure out what the value of the function is there. If it's positive, at that point it's positive throughout that interval. If it's negative, it's negative throughout. We only have to test one point. So we now know which 4 intervals we need to test points on. We should pick a point in each one, test a point in each one, and decide, is that what we want or is that not what we want? Okay. 5. Is it 0 is 5 or is it 0 is 5? It's 2x minus 5. It's not x minus 5. It's 2x minus 5. Which not only is, yeah, it's a little harder, but that is part of the between 5 over 2 and some of the other ones. Okay, if I can draw your attention back, you worked really well on that. I don't know if I can incorporate that more often or not, but I want to be sure to talk about this a little bit more, and there's one other thing to talk about as well. So, where were the zeros here? 3 was one of them. -1. Yeah, pesky little 5 halves. And where exactly is 5 halves?
2.5.
2.5. 2.5. So, and actually here 2.5 is probably a little easier to think of than 5 halves. I mean, they're the same, but for what we're doing, 2.5 is probably a little easier. So we need to pick points in each interval. So over here, there are lots of things we could pick. -2 would work. -3, -27, -pi. The value of the function at -2 we get, well, with the squared, that's always going to be positive. So a positive times a negative times another negative is positive. So the function, whatever it does, goes through this point and is positive over here. How rapidly it goes up, going to the left, or comes down as we look at it going left to right, we don't know. At this point, we don't care. What we care about is we know now the graph was above the x-axis before -1. What about between -1 and 2.5? Is it above or below? It is below. If we check a point, we find out it is below. And again, somewhere in here, if it is below and comes back to 0, we're going to have to go and have a valley. We don't know exactly where. Later on, we will come back to this question of, can we figure out exactly where it has that valley? We're just interested that it's below. And you can pick any point in here, say 0, 0 minus 3 squared, 0 plus 1, 2 times 0 minus 5. That product will be negative. Between 2.5 and 3, or 2.5 and 3, there it's a challenge to actually pick a value that's in there, because there are no nice values in there. 2.6, 2.7, not really nice values, but they are in there. So if we pick, say, 2.6, f at 2.6, well, again, whatever this is squared will always be positive. This is positive. That's just barely positive. The function's positive there. And then if we look past 3, say at, I don't know, 4, that's also positive. So in terms of this particular question, where is this function negative? There's only one interval it's negative, and that's from -1 to 2.5. And notice that is not just, oh, well, one factor has to be negative or another factor. It's a combination of all the factors. I mean, rather than trying to figure out the combination of all the factors, I find it much easier to realize the only place we can change sign is where one of the factors is 0. We identify where the function is 0. We decide what the sign is before the first 0. At one point, if it's positive there, it is positive everywhere. Does it ever switch to negative? Well, it'd have to go through 0. And we found all those places. So if we find all the zeros, between any two zeros, it has to be the same sign. And so let's see. I mean, we could pull out a graphing calculator or some other package to help us here. So we've got x minus 3 squared times x plus 1 times 2x minus 5. And notice here in the graph, it actually is rather a challenge to see what exactly is happening between 2.5 and 3. So here's a case. Now I kind of have to zoom in here to realize, oh, between 2.5 and 3, yes, it is positive. But then I lose this bit of information down here. And so here's a case where there's really not a good window to show us everything we might be interested in. If we really wanted to know where the min is, we need a window this size, but then we kind of lose information about what's happening between 2.5 and 3. So even though a graphing calculator or a graphing utility can produce the graph very readily, if we're not fairly sure of what we're looking for or what we should see there, it's hard to know, how do we highlight those features. But we can solve this inequality and figure out where the original product was negative. Now, the other thing I want to talk about just a little bit is the idea of what's known as rational functions. Sometimes our function involves a division of polynomials. We've got some polynomial divided by another. We will encounter a few of these. We will not do a lot with rational functions. But suppose we had a function for cost. 3x plus 12. If you're making something and you paid $12 or say in a business $12 million to get set up, and then it's $3 million for every million you produce or something with that. You'd have to watch your units, but something in terms of cost, and then the revenue, say 5x minus 10. For advertising and some different things, you don't start earning money right away, but after a while the revenue kicks in, and so we might want to know, well, what's the ratio of revenue to cost? We just take our revenue function divided by the cost function, and we get what's known as a rational expression. Or a rational function. There's some information we're interested in here as well. So with the polynomial, our main information was where is it 0 and where is it positive and negative. We're not yet at all to the point of figuring out where our peaks and valleys are, although at some point we would like to answer that question. We've got quite a bit of calculus to develop before we get to the point of identifying where the peaks and valleys are. But with algebra, we can definitely identify in a polynomial where are we above the axis, where are we below. For rational functions, we're also looking for some short-run behavior. Where do we cross the y-axis? What happens when the input is 0? That we can just plug in. Now, where do we cross the x-axis? For a rational function, where we cross the x-axis is where the numerator is 0. So the y-intercept, what happens when we plug in x equals 0? The x-intercept is where is the function going to equal 0, and it turns out that that's where the numerator is 0. So as long as the numerator is not too complicated, we should be able to figure out, well, where is the numerator 0. But there's this denominator as well, and so there are times where, well, if the denominator is 0, this function is going to have a problem. Where is the denominator 0 for this expression? (3x plus 12 equals 0). Subtract 12 from both sides. Divide both sides by 3. We get x equals -4. Where the denominator is 0, we get a vertical asymptote. The function's not actually defined there, and as long as we're really close to -4, the denominator is really close to 0. And you divide something that's not close to 0 by something that is, you get a big number, either big positive or negative. We're also going to be interested in long-run behavior. Didn't point out with the polynomial, but with polynomials, typically the long-run behavior, well, in fact, the long-run behavior is always determined by the highest degree term, the leading term. So on this one, x minus 3 squared, x plus 1, 2x plus 5. If we multiplied it out, and just focused on what the highest powered terms would be, we get an x squared times another x times a 2x. 2x to the fourth would be the highest powered term. And notice, long range, the two ends look very much like a parabola, x squared, or actually x to the fourth, and even power as well. Even powers always look like this. It's going to look just like the highest powered term. For rationals, the long-run behavior is, well, what happens as x gets really, really, really big? And for that, we look at the leading terms from the numerator and denominator. If the degree of the numerator is bigger than the degree of the denominator, so say this were an x squared and that's an x. If that were the case, the function would go to 0. The denominator gets big a lot quicker than the numerator does. If this degree of the denominator is less, so say this is an x squared and that's an x, the numerator would get big a lot quicker than the denominator, and we wouldn't have any kind of asymptote. The case we're most interested in is when the degree of the numerator and degree of the denominator is the same, which is what happens here. When the degrees are the same, we essentially just have to look at the dominant term in the numerator and denominator. As x is really big, 5 times x minus 10 is not going to be all that much different than 5 times x. 3x plus 12 is not that much different than 3x. So we can drop the rather insignificant portion when x is really big. What is 5x over 3x? X's cancel and we get 5/3. That's our horizontal asymptote. As we head to infinity or minus infinity, we get really close to the curve. Really close to this line. So in fact, the information we've got so far, really the only way we can start by this asymptote, go through these 2 points that we identified and get close to that asymptote, I think is that curve. The other side's a little harder to figure out, although I guess maybe not. If it did this, started by the asymptote and came down to this, well, somewhere we'd have to cross the x-axis. But we've decided it doesn't do that. So it can't be doing this. Well, if it's going to be close to here, this line, and end up close to this line, it's pretty much got to look like that. Because we figured out there are no x-intercepts there, so it's got to be doing this. And so we can come up with a fairly reasonable graph just by analyzing the rational expression a little bit. We will not do a lot of analyzing the rational expression. It's a little bit more than we have time to get into, but we are occasionally going to see some rational expressions. And if we were to graph this, 5x minus 10 divided by 3x plus 12, turn that one off. Change a few things here. It's a little hard to maybe see all the features, and certainly from the graph it's hard to see the features, but we had decided at x equals -4 there should have been a vertical asymptote. And notice that is pretty much what this graph has. To 0 there's an intercept. 0, not quite -1, there's intercept. And we also decided y equals 5/3 should have been a horizontal asymptote. And notice we're pretty accurate with that as well. And so this is a case, even if we can graph it, if we're not careful in the graph, maybe we can recognize there is a vertical asymptote, but we may not know exactly where. If I turn off these asymptotes, I think we kind of realize there is a vertical asymptote, but we may not know where. We may realize it looks like it's leveling out at some value, we just don't know what. Well, the coefficients will enable us to figure that out as we look at the ratio. So we can work with that. So we've got some problems in 1/6 to work on. with rational expressions and with polynomials. See you then on Thursday.